So if you skip part 2 of this lecture and jumped right in with part 3, let's just review for a moment. We have a pair of random variables x, y, and we came up with this measurement called covariance, and and the property of this covariance is that it gives you kind of a scalar notion of what kind of dependency x and y have. Specifically, when covariance is positive, it means that when x goes up, y also tends to go up. And when x is going down, y tends to go down. And doing so, this product term, x minus mu x times y minus mu y, tends to be positive. On the other hand, when covariance is negative, it means that when x is less than its typical value mu x, y tends to have the opposite sign and it tends to be bigger than its mean. So negative covariance means that as x goes down, y tends to go up and vice versa. So our next step was to normalize this covariance by the standard deviation of x and the standard deviation of y. And this gave us a quantity which was dimensionless and between -1 and 1. And then we found out that uh, when rho xy equals -1, it means that typically like y is equal to some ax plus b, where a is less than 0. And rho xy equals 1 implies y is still ax plus b, but a is greater than 0. And finally, we had the case when rho xy equals 0, and that corresponded to x and y independent. In fact, all of these implications are such that y equals ax plus b implies rho is equal to 1 or -1, and xy independent implies rho is 0. We'll see later that there are cases where rho xy, the correlation coefficient, is 0, but x and y aren't actually independent. Just keep in mind that the way to think of this, though, is that this rho is really measuring dependency. And when rho is 0, the dependency could be 0, or at least it's weak. And as rho approaches magnitude 1, the dependency is strong. In fact, the two random variables become the same random variable as the magnitude of rho goes to 1. To understand this a little better, consider the following three plots. In each plot, we have 200 sample XY pairs. Each XY pair is like a little dot. Like for instance, this dot right here corresponds to a sample pair where X is approximately equal to 2 and y is approximately equal to minus 2.1. Other sample pairs, like for instance, a sample pair right up here, would correspond to this sample be x equals 0, y equals 0. And similarly, um, each graph here has 200 of these sample xy pairs, each marked by a little dot. And the difference between the experiments is that in the plot on the left, rho is equal to minus 0.9. In the plot in the middle, rho is equal to 0. In the plot on the right, rho is equal to 0.9. And if you were trying to fit a straight line to this data, you'd, you'd have a straight line through here, and it would approximately be close to y equals 0.9x. And similarly, over here on the right, on the left, when rho is negative 0.9, we see that the xy pairs are again along the straight line, and this straight line happens to be y equals minus 0.9x. On the other hand, when rho is 0, we look in the middle plot and we see that the points here are everywhere. There is no kind of a relationship between the xy pairs. Whatever x you observe, y could be anything. So what the correlation coefficient is measuring is the extent to which the xy pairs are approximately along a straight line. We have one more theorem about the correlation coefficient rho, and that corresponds to the case when we do a units transformation, for instance, where we change x and replace it with ax plus b, and we call that x hat. And we take the data y and we transform it into cy plus d, and we call that y hat. So this corresponds to, for instance, like if X and Y are measuring temperature in Celsius, X hat and Y hat would measure temperature in Fahrenheit. In this case, the covariance is scaled by these constants A and C compared to the original covariance, but because the correlation coefficient is unitless, right? The correlation coefficient in the two systems is the same. So in complicated systems where you can gather data, the correlation coefficient is used or estimated as a way of kind of measuring the dependency between x and y. So for instance, if x is a student's height and y is the same student's weight, we expect the correlation coefficient to be positive, but maybe not too close to 1. People who are taller tend to weigh more. On the other hand, if x is the distance of a phone from the base station and y is the received power of the base station signal at the phone, but that received power is random and depends a lot on the environment you're in. But in general, the farther you are from the base station, the weaker the received power will be. And so power goes down with distance and rho is negative. As a third example, and this is closer to things we've done so far, X is the temperature of a resistor in degrees Celsius. Y is the same temperature in Kelvin. And in this case, rho equals 1 because Y is just a units translation from X. A fourth example, if you have an electrical circuit and you measure the gain as X, but you measure Y as the attenuation in dB, then Y is equal to negative X. And as we would expect, the correlation coefficient is -1. And finally, as a last example, you could imagine, X is your phone number and Y is your social security number. And in this case, your phone number, who knows by what process you were assigned it, and shouldn't have any correlation with your social security number. We'd expect that the correlation coefficient between these two random variables would be 0. So if you followed all that, you understand that covariance is a measure of dependency, and correlation coefficient is the normalized version of that. That's always between -1 and 1. We're now going to introduce a bunch of terminology that's commonly used, and mostly this terminology is just confusing, but it's terminology people use, and so you need to be familiar with it. So the first term is that we talk about the correlation of x and y, and the correlation is denoted R of xy, and it's just equal to E of xy. If you start with covariance of x and y, you have the expected value of x minus mu x, y minus mu y, and if you multiply these terms out, you get xy minus mu y times x minus mu x times y plus mu x mu y. And then you take the expectation term by term, you get E of xy, the correlation, minus mu y ex minus mu x ey plus the expected value of the constant, which is mu x mu y. But this is mu x, and this is mu y. And so get E of xy minus mu x mu y, because we subtract it twice and add it once. So in fact, uh, the covariance is equal to the correlation minus the uh, the product of the expected values. When either mu x or mu y is equal to 0, the correlation is exactly the same as the covariance. So this theorem summarizes properties of correlation. And the first one is the property we just derived, that covariance is equal to correlation minus the product of the expected values. The second property is the theorem that we derived quite a while ago. Variance of x plus y is variance of x plus variance of y plus 2 times covariance. And then finally, if x equals y, then we know that the covariance is equal to the variance of x, which is then equal to the variance of y, since x and y are equal. And this correlation coefficient just happens to be the second moment of x, or equivalently, the second moment of y. In a lot of signal processing applications, E of x squared, or equivalently E of y squared, is called the average power. And it comes from sort of the terminology of circuits, that if x is a voltage, then x squared is the power of the voltage through a 1 ohm resistor. So the fact is, once you start dealing with signals in arbitrary ways, it's whether it's a voltage or a current or a value inside of a computer, we think abstractly as E of x squared as the power of that signal or that random variable. The next bit of funny terminology is the notion of orthogonality. We say that x and y, the random variables, are orthogonal if in fact the correlation of the two random variables is 0. On the other hand, we say that random variables x and y are uncorrelated if the covariance is 0. So remember, covariance 0 means uncorrelated. Correlation equal to 0 means orthogonal. So let's review what we know when random variables x and y are, are independent. The first thing is that all of these properties, these four properties A through D, they really derive from property A. Because in fact, if x and y are independent, then we know that the joint PDF of x and y factors, and this enables us to write step A, that the expected value of g of x times h of y is equal to the double integral of g of x times h of y times the joint PDF of x and y, but that's the product of the marginal PDFs. And then we see that this factors into an integral over x times the integral over y, and we obtain, this is e of g of x, and this is e of h of y. So the property in part A implies part B with g of x equal to x and h of y equal to y. So in that case, what we see is that the correlation of x and y is just equal to e of x times e of y. Similarly, we know that when x and y are independent, we have the covariance is equal to x minus mu x, y minus mu y. And if we call this term gx, and we call this h of y, right? We once again use the part A, and we can say that because of independence, this is e of x minus mu x times e of y minus mu y. And this is 0 times 0, which equals 0. And finally, part D, the variance of x plus y is the variance of x plus the variance of y. And normally we'd have plus 2 times the covariance, but that term is 0 because they're independent. So this slide proves the theorem, and instead of using integrals like we did on the previous slide, it uses PMFs and the PMF factoring into product of marginal PMFs and does summations, but the logic of what's going on is exactly the same. Going back to the noisy observation y equals x plus z, where x is a signal and z is a noise that interferes with the observation or measurement y, if you recall in that example, we had that x was Gaussian with zero mean and standard deviation sigma x, and z was Gaussian with zero mean and standard deviation sigma z, and x and z were independent. The noise in the receiver that z generates is independent of the transmitted signal x. So now we know the following, that x and z being independent implies rho xz equals 0 and covariance xz equals 0. And we're left with finding covariance of x and y and correlation coefficient of rho xy. So to do that, we observe that covariance of x and y is equal to e of xy minus mu x mu y using our previous theorem, right? But we know that mu x equals 0, so this term drops out. And now we observe that ex, we write y is equal to x plus c, right? And so this is equal to e of x squared plus e of x c. And e of x squared is actually equal to variance of x because e of x is equal to 0. And now for this second term, we use the previous theorem, and we know, because we know x and z are independent, e of xc is equal to e of x times e of z. But in fact, both of these terms are 0. So the covariance is equal to sigma x squared. And the correlation coefficient of x and y is equal to the covariance of x and y divided by the square root of the variance of x times the square root of the variance of y. And now we recall that, oh, there's one more term we haven't worked out, and that's the variance of y. But the variance of y is the variance of x plus c, and since x and z are independent, it's equal to variance x plus variance c, so it's sigma x squared plus sigma z squared. So putting these pieces together, we have that the correlation coefficient is equal to sigma x squared over the square root of sigma x squared times the square root of sigma y squared, which is sigma x squared plus sigma z squared. And you can write this in the following way. You can write it as the square root of sigma x squared over sigma x squared plus sigma z squared. And it's convenient at this point to write this as sigma x squared over sigma z squared, 1 plus sigma x squared over sigma z squared. So to summarize, we have the received signal y is the transmitted signal x plus the noise z, and that the correlation coefficient of rho xy is equal to the square root of sigma x squared over sigma z squared over 1 plus sigma x squared over sigma z squared. And now keep in mind that x and z are both zero mean signals. So sigma x squared is the same thing as e of x squared, and that's the average power in x. And sigma z squared is the same thing as e of z squared, since the noise is zero mean. And this is the average noise power. And so sigma x squared over sigma z squared is interpreted as the signal to noise ratio. And people often call this the SNR. And the correlation coefficient, rho xy, between the signal and the observation y, is equal to the signal to noise ratio over 1 plus the signal to noise ratio. And so as the signal to noise ratio goes to infinity, the correlation coefficient is going to 1. Effectively, a signal to noise goes to infinity either by making the signal really strong, right, or by having the noise get very, very weak, right? It corresponds to y getting very close to being exactly equal x and rho getting close to 1. For example, in a communication system, it's not uncommon for SNR to be 10 dB, and this actually corresponds to the value of SNR being 10 and rho being square root of 10 or 11, which is approximately 0.9. Since I'm doing this offline, I just went and did the lookup of square root of 10 or 11, and in fact, it is approximately 0.9. In fact, it's 0.95.